In this video, we're going to look at buffers, which is a big topic on the AP exam. So first you might be asking, what is a buffer or buffered solution? A buffer is something that can resist drastic changes in pH. So it's keeping the pH from changing. It's keeping the pH constant. And you might ask, well, how can we create this? How can we make this happen? So let's consider a weak acid, in this case, HF. Since it's a weak acid, we know a small percent of it ionizes, not 100%. So when we write the ionization reaction, showing it acting as an acid in water, breaking up into H plus and its conjugate base, we write it as a reversible reaction. Since HF is a weak acid, we know its conjugate base is weakly basic because the Ka times the Kb is the Kw. So if you have a weak acid, its conjugate of a base is also weak. And therefore, that's why this is reversible. That's why we can go in the reverse direction where F minus acts as a base, accepts the H plus, because that's what bases do, and turn into HF. So if we have a weak acid, we have this equilibrium reaction that we can write. And now if I only had HF in my container, a very small percent of it would be ionizing. And I would obviously have an acidic pH, right? Now, that itself would not be a buffer. But if I were able to add not just HF into my container, but a source of F minus, and I say a source of F minus because usually we don't have F minus by itself, it's attached to something. So something that would be a source of F minus like NaF, KF, something like that. If I had both of those in my container, then I can harness any changes to H plus by this reaction shifting forward or reverse. So basically kind of harnessing Le Chatelier's principle. So let's talk about that. If I had this solution of HF and F minus, okay, now let's say I add a strong acid into that. I add some sort of source of H plus, which would typically lower the pH, right? And initially, if I add this strong acid, if I add the source of H plus would jump up, right? That would be my stress though. So think about how this reaction would shift. If I add H plus, which way would this reaction shift? It would shift away from it to use it up. So this reaction would shift to the left. And therefore, the H plus would get used up and eventually come back down. Oh, great, the pH change was counteracted. It could stay constant. Well, what about the other direction, right? What if I add a source of OH minus, like a strong base? So if I add a strong base, all of a sudden the OH minus pops up. And you might be like, wait a minute, there's no OH minus in this reaction. However, there is H plus. And what do we know about what H plus and OH minus react to make? They would react to make water. That is, in essence, the net ionic equation of any strong acid, strong base reaction, right? H plus OH minus goes to water. So the H plus would react with this OH minus, and what's happening is essentially the stress is that your H plus is going down, which makes sense. If you're raising, you're putting in OH minus, H plus would come down. Now, what would happen if H plus comes down? This reaction would shift to the right towards it to fill it back up. Oh, great, it fills it back up. The pH change is now counteracted. So as long as you have a source of my weak acid and the conjugate base, you need to intentionally put that in there too, then this reaction can shift either way to counteract either H plus coming up or H plus going down and therefore resist changes in pH. So the takeaway here is you need a weak acid-base pair. And you need enough of them so that you don't run out of going in either direction. Now, some people think of this in two different reactions, and I don't really think of it this way, but you can. If you have both a weak acid and a weak conjugate base in the same container, then the HF, the acid, let's say, if you add OH minus, the acid component can react with the base, right? The acid component can react with the OH minus, and it can counteract that change, right? If we think about HF would act as an acid, it would donate an H to the H plus to the OH minus, the HF would turn into F minus, the OH minus would turn into H2O. You might be like, wait a minute, that's a completely different reaction than what we just talked about. It's actually the same thing, what we just talked about. We said that, hey, if you add an OH minus, it would react with the H plus to make water. And we could think of that as the H plus here coming down. So then we can go looking at this reaction. If I were to add up these two reactions, H plus cancel out, I get the same reaction. This is really the net ionic equation of what we just talked about, what would happen if you add an OH minus. So really what's happening is this reaction going, this reaction still harnessing the same equilibrium that we just talked about. And if I added a strong acid, the base component would react, which in this case would be the F minus, right? The F minus would react with the H plus, it would act as a base, pick up the H plus, and turn into HF, which is in fact the reverse of what we just, this reaction that we have here is the same reaction but going in reverse. So again, you can think of it this way. I like to think of it as you need to harness the equilibrium so that you can apply Le Chatelier's principle. And this is why you need large and roughly equal amounts of HF and F minus. You need large and roughly equal amounts of your weak acid and its conjugate base, or vice versa. So here's just a visual of what I was saying. If you have large and roughly equal amounts of both your weak acid and the conjugate base, or vice versa, weak base and its conjugate acid, then if you were to add H plus, like we had said, you add H plus, this reaction would shift to the left and create more HF. And as long as you start with relatively large amounts, the difference that you started with is really not going to be that big, as long as you start with large amounts. And same thing, if you were to add OH minus, we said, oh, that's the same as like the H plus, coming down, this would shift to the right. So you make more F minus, use up a little of the HF. But again, as long as you start with large amounts, the difference is going to not be that great. And this is kind of almost like that 5% rule where we're saying, oh, like, yes, the amount you make is significant if you look at it by itself, but if you compare it to the initial amount is still relatively unchanged, that kind of thing. But that's why we need to make sure that we do start with a lot. And you want roughly equal because you don't know which way you're going to have to go. You're going to have to use up the base and go to the left in this case. You're going to have to use up the acid, go to the right. And that's why we want both of them in our container in roughly equal quantities. So why does this have to be a weak conjugate acid base pair? Because if you had something like a strong acid, HCl, when we write the ionization reaction, it would be one arrow to the right because we assume it 100% ionizes. This is not a reversible reaction, so it cannot go in the opposite direction. Cl minus is the conjugate of something strong, so it has negligible strength as a base, and that's why it can't accept the H plus and go in reverse. That's why we're writing this one arrow. So if I were to add HCl and even a source of Cl minus, this would never be able to go in the reverse direction. If I add more H plus, it can't go in reverse to counteract that change. So it's never a strong acid and its conjugate base. It's never a strong base and its conjugate acid. We want a weak conjugate acid base pair, and we want both of the components in the solution. Okay, so again, just to summarize, what do we need to make a buffer? We need an approximately equal mixture of large concentrations of a weak acid and its conjugate base, or vice versa. So either like a weak acid HA and its conjugate base A minus, or a weak base, we'll give it the symbol B and its conjugate BH plus. So showing you either way. Here's a base in equilibrium showing the ionization reaction. Remember, usually we make it react with water because the base doesn't have OH minus in it. So that's how we get the OH minus, being produced because the water is acting as the acid and donating the H plus. And notice like 1 molar, 1 molar, 0.9 molar, 1 molar. They don't have to be equal. It actually works best. We say there's optimal buffering if they are equal because obviously you want to be able to go either direction. So a buffer contains the acidic species, which is what's neutralizing the OH minus. It contains a basic species, which is what's neutralizing the H plus. And we need to make sure they're coming from the same equilibrium system, because otherwise, if you add any weak acid and any weak base, then they might react with each other. But if we're doing it from the same equilibrium system, notice that our reactants are on opposite sides. So it's not that they're reacting with each other, if that makes sense. Okay. And as I said, to provide an ion, usually we're not just adding a random ion by itself. It's usually attached to something. So we want it in the form of a soluble salt, so it 100% ionizes. So for instance, if I wanted to provide NH4+, I would attach it to, NH4 is always soluble, so I could really attach it to anything. But if I wanted to, let's say, supply F-, attach it to something like group 1 ion because you know that is always soluble. That's one of your solubility rules you should be remembering, group 1 ammonium nitrate. So the Na+ and F- would 100% ionize, and it would be a source of fully F-. So if it was like 0.1 molar NaF, that's the same as 0.1 molar F-. Your blood is a buffered solution. It ranges in a pH that's relatively close to 7, but buffers don't have to maintain a pH of neutral. It could maintain any pH. It just has to not change to be a buffer. Buffering capacity is the amount of acid or base that can be neutralized before the buffer starts essentially failing as a buffer and starting to have a significant pH change. So before I said we want pretty large concentrations. You can obviously make a buffer if you don't have very large concentrations, but it's not going to last very long. It's not going to resist pH changes for very long because one of your components is going to start to kind of run out. So this is what's called buffering capacity. The greater the concentrations, the greater the buffering capacity. And whenever you're doing a buffer problem, there's this equation called the Henderson-Hasselbalch equation, and this is the buffer equation. You see a question, you identify it as a buffer question, this is likely the equation you have to use. So look at it, find it, it's on your formula sheet. You can always find the pH of a buffer by taking the pKa and adding the log of the concentration of the base over the concentration of the acid component. And notice they have it written as HA for the acid, A minus is the base, but if you're harnessing a weak base and it's conjugate acid, you would just put the base component on top, the acid component on the bottom, and remember those square brackets means molarity, not moles, it's molarity. This equation is actually derived from the Ka expression. So just showing you that is if I took that Ka, which is also on your formula sheet we were using for those weak acid problems, and I would take the negative log of both sides, because you know negative log means we're going to incorporate some P stuff. And remember that I can separate negative logs, or I can separate a log inside. If I have multiplication, I can make that addition. So negative log Ka minus negative log H plus a negative log of the concentration of A minus the conjugate base over the acid. And let's turn this into P's. This is the same as pKa. This is the same as pH. Plus and minus is still minus log A minus over HA, which is the exact same formula you see on your formula sheet. So you don't have to derive this ever. I'm just showing you this is actually the same equation as Ka, just rearranged. And just to notice that since this was derived from Ka, notice that it's always pKa that is in this equation. So if they give you a Kb or pKb in the problem, you might have to convert to a Ka or pKa. So remember that Ka times Kw is, or Ka times Kb is Kw, which is 1 times 10 to the negative 14 at 25 degrees Celsius, or pKa plus pKb equals pKw, which is 14 at 25 degrees Celsius. So again, you might have to convert. They might give you the wrong K. Just be aware it's always Ka for this equation. If you wanted to derive a similar equation for Kb, you could derive it from the Kb expression, just to show you, same thing, separating, taking the negative log of both sides, separating out the negative log of OH. This is pKb, this is POH. Now I have the negative log of the acid component over the base component. You can totally use this equation now. Totally up to you. But I say just use the one on your formula sheet and remember that the base component is on top and the acid component is on the bottom. And if they give you a Ka at Kb, turn it into Ka. Why not? I think that's easier. Take a moment, try this equation or try this question where you're utilizing that equation. Then check your work. Okay, so this is a buffered solution, and notice it's coming from a weak base and it's conjugate acid. It's a source of the conjugate acid in the form of a soluble salt. If I have both of these in my container, I will create a buffer. It says calculate the pH. Anytime I see a buffer equation, if you want, you can write the ionization equation, which is the base. You know, if I want the base on this side, base is reacting with water, and then it's forming its conjugate acid and OH minus. Anytime you see a buffer problem, go straight to writing your Henderson-Hasselbalch equation. You don't even need to know the name of this equation. Just know, oh, there's a buffer equation on my formula sheet. This is it. I have the Kb. Notice because it's a base system that you're more familiar with. You're more familiar with NH3 as a base than NH4 plus as an acid. So I just need to make sure that even though they give me Kb, I'm going to have to get pKb. And it's just going to be my base component in concentration on top over my acid component. So I'm going to rearrange. I'm going to use the fact that Ka times Kb equals Kw, but you could feel free to take the negative log of this and then subtract it from 14 instead. But first I decided to turn this into Ka and take the negative log of that, and I get 9.25. So this 9.25 is going here. The concentrations of each are going top and bottom, and you'll notice molarities cancel out, which is why I don't have units there. And when I do this, I should get 9.05. I want you to start noticing something. Look at my pKa. Look at my pH. Notice how similar they are. Interesting. What would my pH be if I used the same concentration of acid and base? Then I would have the log of 1. Log of 1 is 0. My pH would be my pKa. We're going to start seeing how usually your pH for an optimal buffer will be pKa. And if you have to pick a system, you want to pick a system where the pKa is close to the pH that you want. We'll talk about that in one moment. Okay. Also notice that my pH is 9.05, and it is a roughly basic pH, which kind of makes sense because the Kb of NH3 is 1 times 10 to the negative 1.8 times 10 to the negative 5th, and my Ka for the conjugate acid is 5.6 times 10 to the negative 10th. So my base component is stronger than my acid component, which makes sense that the pH of the buffer lies in the basic range. Okay. Just showing you another way you could do this problem. If you didn't want to use the Henderson-Hasselbalch equation, you could create an icebox with the ionization equation. And initially you have 0.25. Initially, you could assume OH minus. And remember when we were doing this, we would initially assume NH4 plus was 0 when we were doing just like a weak base problem. Instead, this has now become a common ion problem. My NH4 plus is not 0. It is, in this case, we go back to the problem statement, it is 0.4. Okay, so this is very similar to any of those common ion problems we've done before. We could assume that X is so small that these remain unchanged. And if I wanted to, I could plug into my Kb expression, which I have. They gave me the Kb. I can solve for X. In this case, X is OH minus. I can take the negative log of that to get POH. They ask for pH, subtract from 14, and get 9.05. So you can still solve these buffer problems the way you would any weak acid, weak base problem. However, it will become a common ion problem because you not just have the initial acid or base, you have the initial common ion too. And again, you're just using a Kb expression, but we've just come up with this buffer equation, which simplifies it a little bit because it is derived from the same thing. So you can feel free to solve whichever way you like. You're always going to see me using the Henderson-Hasselbalch equation, and eventually when you get to titrations, you're going to see that there is a buffer zone, and whenever you're in the buffer zone, you're going to use this equation too. Okay, so just a note on this last example. The last example, I gave you the concentrations in your solution. However, and you can plug them right in. However, a lot of the time, they'll amend this question to look something like this. A buffered solution is formed by mixing 100 milliliters of 0.25 molar NH3 and 250 milliliters of 0.4 molar NH4Cl. Calculate the pH of the solution. Would my molarities still be 0.25 and 0.40? No, it becomes a mixing problem where once you mix these together, their molarities would change. So my warning to you is sometimes the problem will give the concentrations separately before mixing to create the buffer. You have to first calculate the molarities of each after mixing before you plug in either to this equation or before you plug into your icebox if you're doing that. So how would I do that? I would mole out each component, and then I would divide the moles of each over the new total volume and get the molarities that way. Okay, as we were just starting to talk about, important takeaways. All solutions that have the same ratio of A minus the conjugate base over the conjugate acid, all components that have the same ratio will have the same pH because if you take the log of this number, it'll be the same that you're adding to pKa. Optimal buffering, we say, occurs when these two are equal. Log of 1 gives me 0, and then pH equals pKa. And if you're doing titrations, this is super important because halfway to the equivalence point, halfway until you have used up all the HA to create conjugate base, at the halfway point, you will have equal amounts of these. Your log of this will be, log of 1 is 0, and your pH will be pKa at the half equivalence point, and it's all because of this equation. Okay, now if this fraction starts to change, if you start at 1 and it starts to change, it is not until this fraction changes by a factor of 10, log of 10 is 1, so only when this changes by a factor of 10 will the pH start to change by 1 unit, because you'd be adding log of 10, which is 1. Initially, again, we want to have large concentrations so that we have a large buffering capacity. Buffering capacity is how much buffer do you have so before it starts to kind of run out and not work well. so that this ratio doesn't get changed much. And the pKa for any system should be as close as possible to the pH you want so that you can have an optimal buffer and start with roughly equal concentrations. So take a moment, try this example, then check your work. A chemist needs a solution buffered at 4.3 pH. Which of the following should be chosen? I give you the Ka's. Get used to converting between Ka and pKa. 10 to the taking the negative log of Ka gives you pKa, and if you had to go in reverse, 10 to the negative pKa would be Ka. So I'm going to just take a moment and turn all of these into pKa. So we said to be an optimal buffer, we want the same concentrations of the acid and conjugate base or vice versa. So we want pH to be as close as possible to pKa, so the closest one possible would be benzoic acid. If you wanted to save some time, you could also, rather than doing all these out and doing the pK of all of them, you could do 10 to the negative 4.3 and see which one of these is closest to that number. But this is the way I probably would do it. Now, obviously, sometimes your pH will not match your pKa, whether your measured pH is different or your desired pH is different than the pKa of your system. You can actually still create a buffer, it's just that it won't have optimal buffering, and you will need more of the acid or base component. So if your pH that you want is lower than the pKa of that acid-base conjugate pair system, then the acid form has to have a higher concentration than the base form to make that happen. Logically, this makes sense. If your pH is lower, that means you want more acid, because the acid will give you more H+, and that will lower the pH. But we can also prove this mathematically with the Henderson-Hasselbalch equation. If you have a higher amount of acid than the conjugate base, your denominator is larger than your numerator. So this becomes a number that's smaller than 1. And if you take the log of a number that's smaller than 1, try it in your calculator, you'll get a negative number. So you would be subtracting a number from pKa, and therefore your pH will be lower than your pKa. I don't care if you think of it logically or mathematically, as long as you can rationalize about this, because the AP loves to ask questions about which form would be higher in solution. Or vice versa. If your pH is higher than the pKa, whether the pH you're measuring or desired, if that is higher than the pKa of your system, that means your base form has to have a higher concentration than the acid form in your buffer. And this makes sense because obviously if you have more base, you'll have more OH minus, and that would raise the pH, making sense of why the pH is higher than the pKa. But again, we could prove this mathematically. If your base component, the numerator, is higher than the denominator, that means this will be a number larger than 1. Taking the log of a number larger than 1 is a positive number, and you'll be adding a number to pKa, which makes the pH raise higher than the pKa. So totally makes sense. They love to ask questions about this logically, like we just talked about, or you could also be asked to solve for the ratio or the concentration of an individual species needed to achieve the pH, meaning they give you the pH, they give you the pKa, you have to solve for either this ratio or one of them given the other. So just make sure you're comfortable rearranging this equation, solving for any one of these missing variables. Take a moment, this is a little more conceptual, take a moment, try this example, then check your work. So you want to create a pH, you want a buffer solution that hovers around pH of 4.3. Obviously, these are the same acids as before. We would love to use benzoic acid because the pKa is closest to the pH, but we still could make a buffer from the others. We're just not going to be able to have equal amounts of each to keep the pH at 4.3. So for this one, my pKa is 2.87. My pH is higher than my pKa. So that means I need to have more base component than my acid component. So when I'm creating this solution to keep it around 4.3, I'm going to have more of the base component than the acid. And then this one, my pKa is larger than the pH. So that means I'm going to have more of my acid component to keep the pH around 4.3. And same thing here. This is the this is the lower pKa. The pH is higher than the pKa, so obviously more base. And here, my pH is lower, so more acid. Okay, so conceptual note, and just to kind of wrap this up, if you have all weak acid in your container, it's a weak acid problem. You can use that shortcut equation or the icebox, but you're using the Ka. Very little of it is ionizing into F- for this scenario, and your pH will be less than 7. It's not going to function as a buffer if you have only weak acid in your container and you don't add a separate source of F minus. Now, opposite, if you have all weak base in your container, it's a weak base problem, and your pH is going to be greater than 7. So something like 0.1 molar NH3. If I don't add a source of NH4 plus, the conjugate, it's not going to function as a buffer. It's not going to resist pH changes. It is going to have a pH higher than 7. If I add roughly equal amounts of a weak acid in its conjugate base, or a weak base in its conjugate acid, then it's a buffer problem. It's you can use that Henderson-Hasselbalch equation to calculate the pH, and if I have equal amounts, my pH will be my pKa. It doesn't have to be 7, it doesn't have to be neutral. It all depends on which acid-base pair you are using. The pH will depend on both the pKa and what amounts of acid and base you have in there. You could also do an icebox, but your initial concentrations of the conjugate are not 0. It is a common ion problem. So hopefully this helps to wrap up buffers for you. Do some extra practice. If you didn't do any of the examples in this video, go back and try them. It does take a little bit to get under your belt, and the AP loves to ask questions about picking the right buffer. So, obviously you want the pH close to the pKa. They love to ask questions about if something can act as a buffer. Remember, you want a conjugate acid-base pair, both of them in there, to act as a buffer.